This isn't just biology. This is control. Some organisms don't kill their hosts. They take over their will. A fungus called Cordyceps unilateralis infects ants on the forest floor. It enters the body, spreads through the muscles, and begins to alter behavior. After about 2 to 3 weeks, the ant leaves its colony and moves in unusual ways. It climbs a nearby plant to a specific height. There it locks its jaws onto a leaf in a final grip. Soon after, the ant dies. From its head, the fungus grows and releases spores to infect others below. What's remarkable is how it works. The fungus doesn't control the brain directly. It controls the body. Through chemicals and muscle signals, it turns the ant into a puppet. In the forest, clusters of infected ants can be found at the same height, each one placed with precision, all part of a system designed to spread and survive.
The jewel wasp, Ampulex compressa, hunts cockroaches. Its attack happens in 2 precise steps. The first sting hits the thoracic ganglion, paralyzing the front legs for a few minutes. Then the wasp delivers a second sting through the neck directly into the brain. Using sensory feedback, it targets specific neural centers. This venom doesn't fully paralyze. Instead, it blocks the cockroach's ability to initiate movement. The cockroach can still breathe and respond to touch, but it won't escape. It becomes passive. The wasp leads it by the antenna to a burrow, lays an egg on its body, and seals the entrance. When the larva hatches, it feeds on the host's fluids, then moves inside the body and consumes the organs, all while the host is still alive. Studies show the wasp can precisely detect brain tissue, avoiding other structures. This is a form of natural neurosurgery. The cockroach is not killed immediately. It is kept alive, a fresh, controlled food source for the developing larva.
The flatworm, Leucochloridium paradoxum, begins its cycle inside a bird. Its eggs leave the body through droppings and are later consumed by a snail. Inside the snail, the larvae spread through the body and move into the eye stalks. There they form swollen, pulsating sacs with bright green stripes. The tentacles enlarge, lose the ability to retract, and begin to pulse rhythmically. They mimic a caterpillar or a moving insect. At the same time, the parasite affects the snail's behavior. It reduces its sensitivity to light, pushing it out of the shadows into exposed, elevated places. Now visible, now vulnerable. A bird sees the movement and strikes. It tears off the tentacle and consumes the parasite. The snail often survives. Inside the bird, the parasite matures and begins reproducing. Its eggs are released back into the environment. This is a strategy based on mimicry and behavioral control, turning the host into a living signal, a lure designed to be seen.
A hairworm, such as Paragordius tricuspidatus, begins its life inside a cricket. It enters as a larva and grows within the host, eventually filling most of its body. As it matures, the parasite begins to change behavior. The cricket becomes disoriented, leaving its usual paths and moving in unusual directions. Then comes the second phase. The cricket is driven toward water. When it reaches the edge, it jumps. Often this is fatal. Once in the water, the worm emerges through the body of its host and enters the environment it needs. There it reproduces, forming tangled knots with others of its kind. What makes this even more striking is the timing. The manipulation begins before the parasite is fully mature and continues until the host finds water. In some cases, the cricket survives the exit and lives on for weeks or even months. This is a two-stage strategy. First, disruption, pushing the host toward water. Then, precise control, triggering the final jump at exactly the right moment. All to ensure the parasite reaches the only place where it can reproduce.
A protozoan called Toxoplasma gondii infects rodents by forming cysts in the brain. Once inside, it begins to alter behavior. The mouse becomes less anxious, more exploratory, and less cautious around danger. Its response to predators changes. Instead of avoiding risk, it shows reduced fear, not just toward cats, but toward threats in general. This increases the chance of being caught, and that is exactly the goal, because the cat is the parasite's final host. Inside it, Toxoplasma completes its life cycle and reproduces. What's remarkable is how subtle this control is. The parasite influences brain chemistry and immune responses without causing major damage. Similar effects have been observed in other hosts. This is not direct control, it's behavioral tuning. Lower fear, higher risk. A precise shift that leads the host exactly where the parasite needs it to go. Thank you for watching. Subscribe for more.